Okay, so I believe we are live, and okay, so it's hmm, let me just leave the comments open here. Yeah. Okay, so it's been a while since I looked at the exam questions, but I believe I think there is sort of an informal platform, I'm told, where you can access all the previous year's exam papers and quiz papers and so on. And indeed, this time I think, I don't know if, yeah, I suppose there was once before quiz two, I think I had shared some practice problems. I don't know how helpful that was. That website is what I'm hoping I will build out eventually to have like all the relevant materials. It was supposed to happen with your batch. It's a little unfortunate that I was not able to share with you all the materials that I wanted to. I would still welcome you if you're interested to help me with sort of reviewing and finalizing the new material for the course ahead of the next batch, which I think will only be next year, because I've realized that I do need much more time to make the materials the way I want them to. As a result, you have a much more yeah, I don't know if it's a good thing or a bad thing, but you have fewer things to prepare around essentially. So let me just give you a high level recap of the topics that you're going to look at. So I think we opened with um, way back in week one. I think we started with matroids as a framework for understanding greedy algorithms. So this was sort of one topic that we got into. Then we saw two kinds of reductions. Um, One was max flow based reductions, and the other was NP completeness. So, in the full story that's going to happen in the future, I'll write down in green things you don't have to worry about. So, it's not relevant for the upcoming exam, but these are topics that I hope I hope to have um, a way of sharing them with you in the near future. And if you want to take a look, basically, when we are doing positive reductions, you'll also do SAT and LP based reductions. Um, and this is an interesting thing because SAT is something you normally think of on the hardness side, because we say, that we reduce from SAT, it's a hard problem. But in practice, it turns out that SAT solvers are very powerful. So being able to cast problems in the language of SAT, reductions in the wrong direction, are sometimes surprisingly helpful in the real world. So as heuristics, I think it's a very interesting thing to cover. And along with NP hardness, I want to also focus on something called p-space hardness, which is like a higher complexity class compared to NP. And usually you get to see a lot of games and things like this here. So if you want to prove something about, um, I don't know, things like Tetris or chess and things like that, you'd have to basically go beyond the class NP. So that's stuff that we did not see this time, sadly. But anyway, um, beyond this, I think we basically said we'll talk about approximation. And I think here we have seen mostly LP based, simple LP based rounding. And I don't know if you've seen like greedy. I don't remember if that was covered, but there's some natural arguments that you can make that um, to show things like, for example, in vertex cover, if you do the greedy thing, if you always pick vertices that have maximum degree, right, then you will not get a good approximation. So usually, so back when we talk about greedy, we talk about one thing to think about is greedy fails. Like, when does greedy not work? But you can ask, well, it fails, but is it at least a good approximation? And sometimes the answer is yes, and sometimes the answer is no. So that is something that you can basically analyze on your feet. You don't have to. It's just basically being able to look at an instance, run an algorithm, be imaginative with examples. That's basically what is required. So approximation was one thread. I think then in randomization we only looked at. I think we looked at randomized quicksort, and maybe there's some probability basics. Then I think we went on to, we have some exact algorithms. Did you encounter the material about dynamic programming and tree width based DP?
Ma'am, dynamic programming. I think
Um,
we came across lectures which incorporated dynamic programming,
Correct.
but we didn't come like across any lecture which started with it. So
No, not started. I think DP. I think, yeah, I had some material before, but I thought it was repetitive, so I think we may not have released that. But
right.
you've seen tree width, right, as a concept, tree width and path width.
Yes, ma'am. Tree width I can remember, ma'am. Yeah.
Yeah, it should be there. I think we
Yeah.
released it in one of the weeks. Yeah, sorry. I'm also like, because I'm in this whatever zone of revamping the material, half of the stuff in my folder is saved as old, new, 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 really new. It's like my version control is terrible on this. So yeah, unfortunately I've also sort of started losing track a little bit. But anyway, I think let me sorry, just give me 1 second. Mm, yeah, okay. Sorry. Right. So there are exact algorithms, and there should have been material that you see on TreeWith, and I think that is one of the few things that we do that I would say is like a non-trivial. It's a little bit of a challenging thing conceptually. So if you haven't had a chance to, then please do spend some time on that. And then I think we saw the parameterized paradigm. I'm just trying to see how I make room for writing that down, but maybe I'll just try to squeeze it in here. Um, and Ismay, I think the main thing we saw was, I think, may have seen a little bit of branching and iterative compression. And yeah, I think in the quiz, for example, the second quiz, the main emphasis was on iterative compression as a method. So yeah, essentially, I think these were all the topics we looked at. I think there wasn't like there is basically. I think the stuff that is missing is what we wanted to also cover was examples of approximation plus randomization, randomization plus parameterized or FPT, and parameterized approximation. So we wanted to cover basically one example of each of these. So for example, when you do LP rounding, you basically say, well, instead of rounding deterministically as we do, so I can just give you like in 5 minutes a flavor of the kinds of things that we wanted to do but we did not. So let's say your LP gives your variables some fractional value. So for example, let's say xi ends up being like a 0.7 or something. So you can say, so normally our rounding has been things like if xi is bigger than half or maybe greater than or equal to half, set xi rounded maybe to 1. And if xi is less than half, then set the rounded version of xi to 0. So this is the kind of like, this is So this is what you would call, um, fixed threshold rounding. So your threshold is some absolute constant. In this case, it's half. But in many cases, it helps to do either adaptive rounding, where you don't fix the threshold up front. The threshold is something that evolves with the algorithm itself. So that's adaptive. But you can also do randomized rounding. And in this example, for instance, I could say, well, I will round xi to 1 with probability xi. So that's a very interesting idea, that xi prime or xi tilde or whatever, the rounded value of xi is set to 1 with probability xi. So with probability 70%, in this example, I will set, so I'm setting xi to 1 most of the time, but not all of the time. And then what can you say about such an algorithm? This becomes now a randomized algorithm. And you will start thinking about, approximation ratios and expectation, or with high probability and things like that. So, so that would be an example of saying randomized and approximation combined. There are many other ways in which these paradigms combine, but the one I wanted to tell you about in this course was randomized rounding. So LP rounding is something you've seen fixed threshold rounding. And I wanted to think about what happens when you round, but using a random process instead, right? So that is randomized approximation. Parameterized and randomized is also like a really cool combination. So basically, random events can be used to guide, parameterized algorithms. So one very famous example of this is something called color coding. Again, because this is out of syllabus in this edition of the course, I won't spend too much time on the details, but at a very high level, the traditional example given for this is k-path. So suppose you want to know if there exists a path on k vertices in your graph, V1. And this is hard because it's if you set k to n, you get Hamiltonian path. So it's hard by generalization because it has Hamiltonian path as a special case. So this is a hard problem. So you're trying to look for a path of length k. And what the algorithm does is it says, well, color the graph, take every vertex of the graph and color it randomly with one of k colors. So you have a graph that is partitioned into k color classes, and this is a random partition. And in this random partition, you ask a related question, which is, can I find a path which has one vertex in each color class? So can I find a colorful path? So it turns out, for reasons that I won't get into, looking for a colorful path is an easier exercise than looking for a path in the original graph. Look for a colorful path, whatever that means. And this is easier to do. The problem is that it's possible that your graph has a path of length k, but in your random coloring, the vertices of that path were not colorful. They did not all get colored with different colors. So you want to think about, when that happens, you call it like the bad event. The bad event is there was a path, let's say, and instead of getting, red, blue, green, yellow, this would be a good event. But maybe in your random coloring, because the coloring is random, anything can happen. So maybe this happened, and this is a bad coloring because it prevents this path from getting discovered. So you say that the bad events happen with low probability, and if there is a path with high probability, the path will emerge as being colorful. And once you're only looking for colorful paths, life is much simpler somehow. So it's then a straightforward dynamic programming exercise, and things work out quite nicely. So this is a classic example of how randomization combines with parameterized algorithms. What remains is parameterized approximation. And here I won't give you any concrete examples because it's a little, beyond the scope of this discussion. But basically, there is an issue of hardness even in the parameterized world. So you may have problems that are hard to approximate. So for example, vertex cover is widely believed to not have an approximation ratio better than 2, meaning that it's widely believed that there is no polynomial time algorithm that can in a guaranteed fashion approximate vertex cover to a factor of c where c is strictly smaller than 2. So there are problems that are hard to approximate for some approximation ratio. And then there are problems that are W hard, meaning no FPT algorithms expected under reasonable assumptions. So this is hard. So you're hard in the parameterized world and you're also hard in the approximation world. So we tell ourselves, well, here we are restricting ourselves to p-time algorithms, and here we are restricting ourselves to exact answers or exact solutions. So what if we combine the two relaxations and we say, take FPT time and output an approximate answer. So this opens up a whole new world of possibilities, right? It tells you that, because you are no longer, now you can combine the best or worst of both worlds, depending on how you view it. But basically, you're now combining two compromises and you're saying, chalo, it's okay, take your time, let's not restrict ourselves to polynomial time, which is what you would do in the approximation world. And in the world of FPT algorithms, you would be insistent on getting the exact solution. There's no compromise on the quality of the solution. But since an FPT algorithm is not expected, you say, okay, maybe I don't want an exact solution. Give me an approximate solution. So again, approximate in polynomial time is not possible. Exact in FPT time is not possible. But what if I give you both? I give you the flexibility to output an approximate answer, and I give you more than polynomial time. I give you FPT time. Then it turns out that some of these really notoriously hard problems actually can be cracked, and there are some very interesting algorithms in this space. So I had one or two examples in mind for the full version of this course. So basically, that's an overview of all the things that I was really hoping to do with all of you, but unfortunately, because of circumstances mostly beyond my control, that's the material that we were not able to release this semester. But if any of you are curious enough and interested enough, feel free to hit me up for, we can work on it informally or through the modality of a project. I'm happy to work with you one-on-one as I try to clean up my material. So I have some scattered recordings, I have some scattered notes. I'm just trying to bring everything together. I think it was overambitious for me to say that I would have done it in time for you guys. That's just an error of judgment on my part. So the next edition of this course will hopefully have these 3 extra examples and algorithms that we were not able to do spread over the last 3 weeks. But coming back to what's much more relevant for all of you, I think, thanks so much, folks. Yeah, and thanks also for your sort of understanding and patience with this. So yeah, I'd love to. I know that there are some emails that I actually haven't gotten back to yet, and I do plan to. But beyond that, it's definitely an open invitation for those of you who are on the call and for any of you who might be watching the recording later. If any of what I said in the last 10 minutes or so is interesting to you guys, and you actually feel like you wish you could have done it as a part of the course and we couldn't, then I'm very happy to do it over the next few months, because I'll be working on it anyway. We are not offering advanced algo next term. We'll be offering it only next year. So in the coming term, I'll try to do my homework. So I'll be very happy to have some company and get some feedback. And yeah, so that's how I hope to make up for it a little bit. And in the meantime, for the exam that's upcoming on Sunday, it's going to be fairly straightforward. In fact, it's a little easier than the previous editions in the sense that I think the 2 things that we were doing previously, because I wanted to make room for all this new material, I said, let's not release that other material. So we did basic greedy algorithms with stable matchings, and we did, I think, an introduction to basic dynamic programming through examples like knapsack and so on. So I think those two are actually not in the syllabus anymore. So you don't have to worry about recapping that. I think if you just recap the topics you can see on your screen, basically matroids, be comfortable with NP completeness reductions, max flow. So essentially the preparation that you did for quiz 1 and quiz 2 should broadly be enough. The only extra topic I think is going to be this business about tree width and path width. I think those videos should have reached you. Make sure that you double check once. And I will definitely release, just like I did for quiz 2, I think I will release a problem set, which should, I think which if you just eyeball it and make sure that you sanity check it, then you should be good for the exam, I think. So just maybe mark off like 2-3 hours of revision on like tomorrow or Saturday and just go over the problem set. And I think that should be that should have you all set for the exam. I know that there was, I think on the forum, I remember that I tried to reply to questions that came up, but I think there was an unresolved thread about cluster vertex deletion. We could work through that right now. But before we go there, because that's a discussion on its own right, are there any other specific questions that I can address? Then, please let me know. But basically, quiz 1, quiz 2 prep, plus make sure that some dynamic programming, I think there was dynamic programming over subsets and dynamic programming over tree decompositions, path decompositions. That should have been 1 week of material somewhere in there. If you can't find it, let me know. But I'm pretty confident because I remember discussing with maybe Arup or somebody on the call can confirm that that material was released. And so that's definitely a part of the syllabus. So if you haven't had a chance to do it so far, then please take a look. But otherwise, yeah, basically this is it. So this is what you need to watch out for. So before we go into the details of cluster vertex deletion, which will probably take me another 15-20 minutes to cover, is there anything else that I can address? Feel free to unmute or drop your questions in the chat. I'm watching out on both.
Ma'am, this is not a question, but actually I wanted to say thank you for the questions you provided us for like quiz 2 prep. They were really handy, ma'am. They were really handy. So thank you for that.
Okay. All right. I'm glad that was helpful. Thanks for confirming. And very happy to do something similar for the exam. So you should have an update from me or the team later tonight or latest by tomorrow morning.
Thank you.
Okay.
One more thing, ma'am. This is also not
Yes.
a question. I agree to him that the questions were really helpful, and it's just a feedback that I really loved the course, and it was really sad when we didn't get new videos. I did write in the G space as well about it, and
Oh,
I plan on watching the videos whenever they come in future. So yeah, that is what I plan on doing. And ma'am, if I would also like to help out in any way if it is possible.
okay. That's so awesome. Yeah. Thank you so much. Yeah. I think that's, it's really good motivation for me to just, get my act together and pull up my socks a little bit. I think, basically it's just, I think, not being able to estimate properly in spite of having done this before. I think I always tend to be very enthusiastic and imagine they'll get done. So I think the recordings have mostly happened, but it's really the edits that have been a little bit, a little bit
Yeah,
painful to
that
work
I
with.
assumed
So,
actually. But yeah,
yeah.
thank you.
Right, right. So, no, I really appreciate the offers for help, and I will not probably, but quite certainly reach out to all of you, and definitely keep you posted when the new materials come in. And the hope is that by I know these are famous last words, but the hope is that by the next edition of the course, it'll be a complete package in terms of a fairly decent question bank plus. Lecture notes for people who may prefer to read over watching videos, and videos for those who like the videos. And we are even trying to see if we can release like Notebook LM links to this material, because NotebookLM in my experiments has been pretty good with synthesizing the content, and then that way you have an interactive tutor kind of an experience. So
Yes.
we just need to train it, pre-train it a little bit, and I think that should be a good interface to this material. But and that's also why I really want to build out the course notes, because NotebookLM, I think, parses notes a little better than video. So the hope is to kind of consolidate everything and have it all ready, which is why I think we are skipping one term, so that I just have enough buffer time to, actually put everything together. And yeah, I think if we have some of you on board, if you have the time to take a look informally, definitely really appreciate that. So thanks a ton, all of you. And yeah, like I said, my apologies for the lapses. Like I said, hopefully the fact that we can keep in touch beyond the course will make up for it a little bit. So, all right. So I think the one last thing, I'm not sure if, yeah, hopefully a good idea to actually talk about cluster vertex deletion a little bit. Let me just see if I have context on the question. Um, So cluster vertex deletion, at least, yeah, I'm just trying to locate any specific doubts that people may have had. But yeah, maybe let's just walk through the problem and at least the natural things that come up intuitively. Um, so CVD is like an extension a little bit of vertex cover. And remember, in iterative compression, I think it's reasonable to focus on the compression step. The compression step is that you have here a solution of size k plus 1. We could call this S. And what's left in this example, since this is CVD, what's left is essentially a disjoint union of cliques. So this is some, I should probably draw a few more of these, but for now, this is, let's say, some, I don't know, CQ number of cliques, I guess. Right, so each of these components is a complete graph, and there are no edges across the green blobs, so these are all disjoint. This generalization of vertex cover in the sense that vertex cover can be thought of as all these cliques having size 1, single vertex, singleton sized cliques essentially. But this is a little more general than that. And as usual, what we are trying to do is say we have a solution of size k plus 1. So we kind of guess. We're looking for some optimal solution. Let's call that S star. We don't know what S star looks like, but we can afford to try all possibilities for S star intersection S. Okay, so let's call this Y. Y is short for yes. We are picking these fellows in our new solution. So that's Y. And then the rest of it we can say is N. These are things that are forbidden from being chosen. We don't want to pick these guys in the new solution. So one of the things is that the graph induced by N itself should be a cluster graph, because we are not allowed to delete anything from here. So if we have a problem here, we don't have a chance to fix it. Okay, so so essentially the problem boils down to the following problem now. Okay, you have, just like disjoint forests for FES, you have a bunch of clusters here. This is the forbidden set. And then you have a larger graph on the outside. So the size of this set is at most k, or possibly even k plus 1. But yeah, this is the small set. And this is the large. This is like wild, wild west. This is the large cluster graph, which was G minus S. Okay. So now you have a whole bunch of clusters here. And now, of course, we could have, like, the union of these two need not be a cluster graph, right? Because you could have, like, what's problematic is when you have edges going across, right? This is going to be an issue. And now the question is, what's the smallest footprint? Like, basically, what's the smallest number of things I can delete from here so that everything becomes like a nice cluster graph overall? So I believe this was the setup that we had for cluster vertex deletion. Let me see if okay, so on the problem set on the website, I have split vertex deletion, but I don't have. So was the doubt about cluster vertex deletion, split vertex deletion? I can't remember. Like, split would be basically the same thing, except we're working with split graphs instead of cluster graphs. But let me just try. Okay, so in the quiz, I think it was cluster vertex deletion, right? And the first question in this, okay, so this is the setting. If anybody has doubts with the setup or the definitions, then let me know. But hopefully we are good on that. So the first question was, a graph is a cluster graph if and only if it does not have an induced path on 3 vertices. And I hope, like, the notion of an induced path is clear. So basically, so this is a path on 3 vertices, x, y, z. And by an induced path, basically what we mean is, yeah, let me maybe draw a fuller example. So let's say this is w, x, y, z. So notice that x, y, z in this graph is a path on 3 vertices. Would argue this. But it's not an induced path, because there is an induced path has to be a pure path, in the sense that if I just look at those 3 vertices, let's erase W, I'm only looking at the subgraph. The subgraph has to precisely be a path, meaning this edge here should not be there. Okay? So it's basically a path, but not a triangle, is how you can think of it. Okay. On the other hand, is there an induced path here on 3 vertices? Well, let's see. What if I take, for example, WXY? So if I were to, so actually, let me just make copies of this. Yeah, so if I look at XYZ, I see that it's not purely a path. But if I look at WXY, for example, and I delete Z, I see that this is purely a path and nothing else. And similarly, if I were to delete Y, okay, so if I were to delete Y, That's not an induced path again, it's a triangle. What else can I delete? So here I've deleted W, here I've deleted Z, here I've deleted Y, so I can also delete X. So if I delete X, then again, you can see that I'm left with precisely a path and nothing else, right? So basically these would be the subgraphs that are induced paths. The other two are not, even though you might say, oh, this is a path like X, Z, Y is a path on 3 vertices. These are paths, but it's not only a path. There is some extra noise there from the other edges. So those are not considered. Those are not called induced paths. Okay, so so hopefully the terminology is clear. So now we want to say that a graph is a cluster graph if and only if it does not have an induced path on 3 vertices. Okay, so let's try and so it turns out that this claim is actually true. And let's try and see if we can prove both directions. All right, so okay, so if a graph is a cluster graph, then it looks like that. It's a disjoint union of cliques. Now, how can you pick 3 vertices? Well, all your 3 vertices may be in different cliques, in which case the induced subgraph on them will look like an independent set. It doesn't look like a path at all. You could have 2 vertices in one clique and one in the other, in which case your induced, oops, sorry, think I ended up killing my Google Meet. Let me just rejoin. Okay. Right. So if you have 2 vertices in a single component and the third from, like basically we are trying to say, okay, take any 3 vertices. How can they show up? And in all cases, we're going to say, look, it doesn't look like a path, right? So if it shows up as 2 vertices in one component and one in a different component, then it's certainly not a path. It's an edge and isolated vertex. And of course, if all 3 vertices are in a single component, then it doesn't look like a path either, because it looks like a triangle. So those are not considered induced paths. So because that would be a triangle. So if you are a cluster graph, then you don't have any induced paths on 3 vertices. This is done. Now, suppose you have no induced path on 3 vertices, then we want to show that you are a cluster graph. And let's see if it's easier to show a contrapositive. Okay, so by contrapositive, I mean the following. So I want to say no induced path. So no induced P3 implies the graph is a cluster graph. So the contrapositive would be that if the graph is not a cluster graph, then there exists an induced P3. So this is an equivalent statement. And let's try and see if we can show this. So if you're not a cluster graph, that means that there exists a component which is not a clique, right? And a connected component that is not a clique has to have at least 3 vertices, because if you're a singleton or if you are 2 vertices, for 2 vertices to be a connected component, it has to be an edge. So So basically, you cannot be a component on one or two vertices and not be a clique. Those are automatically cliques. So if you are a component that is not a clique, then you definitely have at least three vertices, right? You have at least three vertices. And what do we know when we say it's not a clique? Then what we know is ki kahin na kahin there's a missing edge, right? Some edge is definitely missing because we are assuming that this is a non-clique component. So sorry, let me just make some room for myself. Oops. Okay, I think the lasso tool is a bit edgy around the border, so I'll fix that manually. Yeah, so this is some connected component that is not a clique. It's not a clique. And because it's not a clique, by definition, not every edge is present. And let's say this was the missing edge. But because it's a connected component, we know that between U and V, there must be some path. Because it's a connected component, there must be some path. And let's then look at the shortest path. Among all possible paths, let's find the shortest one. And let's say that this was the shortest path. Then we know, for example, that yeah, let's just take the first three vertices on this path. Okay. And these three vertices, I claim that these three vertices must together form a P3, an induced P3, because if not, well, they already have these two edges. If it's not an induced P3, that means that this edge is also present. That's why it's not an induced P3. But if that edge is present, then I can short circuit and make this path smaller, right? So that would violate our assumption that we have a shortest path. And in particular, of course, it's possible that you have a non-edge between U and V, and the shortest path just has length 2, is W, which is fine. Then this is your induced path. Okay. Excuse me. So the path connecting U and V has to have at least three vertices. It cannot have two because by assumption UV is not an edge. So there is no direct connection. So even if it's a single hop connection, you've immediately found your P3. If it's not a single hop connection, if it's a longer path, then take the shortest path, and the first three vertices on that shortest path will form an induced P3. So we have shown that if a graph is not a cluster graph, then it must have an induced P3. The contrapositive is that if there are no induced P3s, then you must be a cluster graph. So this presence of an induced path of length 3 completely characterizes cluster graphs. Okay, so now this is nice because it's just an immediate algorithm, both from approximation and parameterized points of view. So if you want to find if you want to delete vertices so that you want to remove some subset of vertices so that the rest of it is a cluster graph, then you basically take your input graph, G, this is your big graph, and you try to basically find a P3. If there is no P3, you're immediately done because it's already a cluster graph and there's nothing to do. But if you have found a P3, then you can say, well, this P3 must be destroyed. So you could say, for example, branch on G minus A, K minus 1. Branching, I just mean recursively solve the following. So this is like a exhaustive, effectively an exhaustive search. What we are saying is that any solution to the CVD problem must pick A, B, or C, because if you haven't destroyed this P3, then you haven't gotten a cluster graph yet. So we know that one of these three vertices definitely belongs to any solution, and in particular the optimal solution. We don't know which combination of vertices from ABC are going into the optimal solution, but that's okay. We can try all of them. And so you go into three parallel universes. In the first one, you say I pick A, in the second, you pick B, in the third, you pick C. And because you've made a choice, your budget reduces by 1. You had a budget of K, it becomes K minus 1. So this becomes a search tree with depth K and a branching factor of 3. So this is like a 3 to the K FPT algorithm for this problem. The other thing you can do is to say that, well, just pick all three, right? Let's be greedy and pick all three. Pick all three and recurse on G minus ABC. Now this will give you a 3 approximation, because we know that opt will pick at least 1 and we are picking at most 3 in every iteration. So if you take this equation and sum it over all iterations, you will see that the output is at most 3 times opt. So already the answer to that first question alone in the exam or in the quiz, the first part says show that, or whatever it says, is it true that graph is a cluster graph if and only if it has no induced P3s. Once you show that, that immediately gives you a FPT algorithm, it gives you a 3 approximation, but it also gives you many ideas for executing iterative compression, as we will see in the next parts. But okay, you might wonder that, I don't know if you have not seen this proof before. Was I kind of expecting that you come up with all of these ideas in a timed quiz? Perhaps not. I think if you've seen it before, it's definitely, then it becomes fact recall kind of a question. If you haven't seen it before, what I was hoping would happen is that you would play around with a few examples. And although this is not ideal and not mathematically, robust to say that, okay, if something holds for a few examples, that it can be extrapolated, that's often not the case. So examples can be misleading. But in this case, I was hoping that the examples might actually give you some intuition for how a proof would work. So you may not do a proof in writing or in your head at this level of detail that we just discussed. But basically, the hope would be that in an exam setting, you can still kind of anticipate that, okay, maybe something like this should work. So one direction I think is easy. Where you see a cluster graph, you definitely don't see P3s. I think that one-way implication is pakka. It's the reverse that's a bit harder, where you say, oh, if you don't have P3s, can you be sure that you have a cluster graph? And there, I think the idea of working with a contrapositive may or may not occur to you, but I think this is where maybe working with a few examples is useful. Like, how can you have a P3 if it's a cluster graph? And messing around with that a little bit gives you enough of a clue to go all in on the claim. But now, basically, I think the game becomes, when you are looking at this forbidden substructure problem, you basically start thinking about how are these P3s laid out. So then it becomes very similar in style to the kind of arguments you were doing for FVS, right? So for FVS, we had this degree 2 short circuiting and things like that. And here, like, basically, if you see a forbidden thing where 2 elements of the forbidden induced path are upstairs and only one is downstairs, then what is down has to be forced. Right. So basically, the rest of the questions in this quiz, we're basically trying to build on this idea. So, excuse me, my guess is, I'm not sure who had the doubt about CVD, but my guess is that it may have been a starting problem. So if this part is clear, hopefully the rest of it is also clear. And I think it may be a nice practice thing to do. I don't know if you have access to the questions that came in the quiz. I can post them again if that helps. But But basically, I think it's a fun thing to do to now go back to the CBD question and try to solve the remaining parts, because I think they're all small puzzles that you should now be able to work out based on the idea that cluster graph exactly corresponds to absence of induced P3. So let me know if that makes sense. Let me know if you want me to spend a little more time going into some of the specific questions. I'm happy to do that, but it's just that we are a little close to being on the hour, and I know you have not just advanced algo, but probably other exams as well. So I don't want to keep you right now. Like I said, I'd be very excited to continue our conversations beyond the end of the formal course. So we could pick this up. We'll also pick this up later, but I'm not constrained for time. So if anybody wants me to go a little deeper into any of the specifics, please let me know. Okay, but if not, then I think you will have access to a recording of what we just discussed. I believe that should be available more or less. I don't know if immediately, but soon after the session, I think, and hopefully you have enough hints now to pursue the rest of the parts. And I think with this, maybe it also helps to go back to I think the practice set there was split vertex deletion should also probably make more sense now. I'm not sure if um, basically, I think it's analogous in many ways, but the details are different. The overall framework is kind of very similar. So, yeah, okay. I hope that helps. I don't know if some of the confusion was because the difference between a path and an induced path is not clear, and I don't. Again, right now I'm not sure if that was explicitly discussed before or not, but at least now you know. So that's something, I guess. But anyway, so let's okay, thanks, Shreya, that's helpful. And yeah let's uh, let's maybe catch up. I'd love to keep in touch. I think this term just flew by from my perspective because it's just playing catch up. But I hope even though you saw sort of a censored, unintentionally censored version of the course, I hope that you still learned something from it and had a good time. And I look forward to your help in developing the full version as we go along in the coming weeks. In the meantime, I'd like to wish all of you all the very best for your upcoming exams and anything else that you might be dealing with right now. And so I guess we could call it a wrap with that. We're just about going to be on the hour, so it's probably a good time to call it an evening. But yeah, any pending emails, messages, and discourse, I promise to be following up very soon. And I will be a little extra alert in the over the coming weekend. So please feel free to reach out if you have any questions. All right, everybody. Thanks so much. And thanks so much for joining in real time, especially Shreya, Satyaki, and Suyash. Appreciate your company here. Good night for now and see you soon. Thanks.
Not
Okay.
just a question that we would be getting the practice problems for end term by tomorrow.
By tonight or tomorrow morning at the latest.
Okay,
Yes. Yeah.
yeah, thank you.
Okay. All right. Thanks. All right.